The next ranking member.
Who's the next ranking member?
Someone who knows Madi well.
Not me.
Yeah. Okay, I think it's.
Is this the dry run for the prelim?
Yeah.
So this is pretty much what you have in mind.
Yes.
So I'm gonna give you feedback based on this, okay?
Yeah.
That's your introduction.
Okay, so today we have Madi Zholbaryssov, a PhD candidate at ETH Illinois, talking about distributed control for microgrids. Madi, go ahead and start whenever you're ready.
Thank you. Welcome to the seminar. So today I will talk about the distributed strategies for generation control of islanded AC microgrids over time-varying communication networks. So I will. Can I click? I will give my motivation for considering this problem. Then I will explain my motivation for this problem, and then move to the main part where I'm going to present the control strategies, and we'll conclude with the numerical results. So as you all know, there are many benefits that microgrids can offer. They can provide higher power quality. They can disconnect from the bulk grid if the power from the bulk grid is of poor quality. They can provide backup generation when the bulk grid is unavailable. And shorter lines in the microgrids results in higher efficiency. And also microgrids can provide flexibility in many forms and shapes, and mainly the flexibility comes from the fast responsiveness of distributed generators, flexible loads, and energy storage devices. And the integration of renewables through microgrids reduces the greenhouse gas emissions. And these are the main benefits. So these benefits are the main reasons why we are gradually moving away from the centralized power generation to more decentralized. But to materialize these benefits, we need to design control systems so that they can achieve the following objectives. So first objective is proportional power sharing. Basically, we need to allocate power among generators in some desired way, and regulate frequency, maintain frequency at 60 Hertz, and minimize the generation costs. So over the years, different control systems have been proposed to address these objectives. And mostly, so they rely on communication networks with either a centralized or distributed architecture. Centralized control systems rely on a central processor to which information is communicated from different locations for control purposes. And then the central processor computes the control commands and sends them back to distributed generators. However, failure of a central processor might cause the collapse of the control system. And to make the control system more resilient against such failures, distributed implementation is needed, in which each bus has a local processing unit which is capable of performing computations and can communicate with other units at neighboring buses. And in typically distributed architecture imposes less strict requirements on the sensing and communication ranges of the devices. And Also, distributed architecture allows to create flexible plug-and-play system, which is more adaptable to network changes and easier to scale. However, there are challenges that distributed implementation poses. And one challenge is how to coordinate distributed generators such that the coordination is resilient against communication delays and packet drops. And another challenge comes from the convergence speed, how to ensure fast convergence so that they can provide timely response to disturbances. So in this work, I adopt the following model. So I assume that the system is in balanced three-phase sinusoidal regime. Each distributed energy resource, DER, interface with the inverter is modeled as a controlled voltage source behind reactance with adjustable voltage magnitude and frequency. And for stability analysis, I assume that voltage magnitudes are fixed. But in the numerical simulations, there is a voltage controller, and we show that the frequency controller will be able to achieve objectives under the voltage variations. And we assume that the loads are constant power loads. So once we treat each DER as a controlled voltage source, microgrid dynamics can be described by differential and algebraic equations, where we have a control signal by which we adjust frequency, and these phase angles are in the reference frame, which is rotating with the nominal speed. Now, once we differentiate this, the power flow equations, we arrive at ODE model. And these two models are equivalent as long as the submatrix of the weighted Laplacian or Jacobian of the power flow equations corresponding to loads is invertible. So we are going to propose control strategies for this model. Here I introduce the cyber layer that we are using. I consider two cases. So the first case, when the communication graph GIK is undirected, so all communication links are bidirectional. So this graph has an edge set, epsilon ik, which includes all edges corresponding to active communication links. So this graph is time varying. And
Among the inverters, yes.
Among the inverters, yes. Cyber layer, yes. Among the inverters. So ij belongs to this edge set if nodes I and j simultaneously exchange information with each other during time interval tk plus 1. And there is another edge set, epsilon subscript infinity is the edge set, is the set of all communication links. Okay, and each communication link in this edge set is established infinitely often. And I denotes the set of neighbors of node I.
So the infinity set you have there, it doesn't mean that you have a all-to-all graph, right? That's basically the nominal case if the communications were working properly at all times, right?
Yes. Yeah. And similarly, we consider directed case when communication graph is directed, and here edge ij belongs to this set epsilon ik, if node J receives information from node I during time interval tk plus 1, so communication link now is unidirectional. And in a similar way, we also define this H set epsilon infinity. And the sets of out neighbors and in neighbors of node I are denoted by Ni superscript plus, Ni superscript minus. And regarding the communication network, I'm going to make two assumptions. These are very standard assumptions to make. So the first assumption is that communication link between nodes I and J is established at least once every B iterations, where B is some bounded number. So I make this assumption for undirected and directed communication graph. And then the second assumption for undirected graph is that the edges in this set, which you remember, it's a set of all communication links. The edges of this set form a connected graph. Now, for directed case, we assume that the edges form a strongly connected graph. So, which means that if a node has a valuable information, this information should reach any other node through a path formed by the communication links.
I don't understand assumption 2. Why do you have the if statement there?
This is when, maybe more like when for GIK directed, this is what we have to make.
Right. But,
Yeah.
Right. I see what you're saying.
Yeah.
But these are different. Yeah. Okay.
Yeah. Okay. So.
Go back up one.
Yeah.
So that
Yeah.
persistent information transmission is that goes back to Yapapa's paper, where the union of the graphs over time need to be connected.
Yeah.
Right?
Yeah.
That's what is that how they called it? The persistent information transmission. I don't think it's called
Yeah,
that
I
way.
think maybe not. Yeah.
Okay.
Different papers call it differently.
Right.
Yeah.
But make sure that you acknowledge these things.
Okay.
So,
Yeah.
okay.
Yeah. So these are the standard assumptions.
Agree.
Yeah.
Standard assumptions in this set of literature.
Yeah, in the set of which, yeah. In the so we design a control strategies so that we achieve these control objectives. The first objective is proportional power sharing. So consumed power needs to be allocated among generators in some desired way, and which is specified by these inverse Drup coefficients, di for generator I. And these inverse Drup coefficients can be specified in several ways. One way is based on the power ratings of the generator. So the generator with the largest amount of capacity produces largest amount of power. Or these coefficients can be chosen in some other economically optimal way, which can be computed by the tertiary control layer by solving an optimal power flow problem. And the second objective is to maintain frequency at its nominal value. So these are the main objectives in this talk. Okay, and there are numerous distributed approaches that have been proposed to solve the generation control problem. For example, paper from 2014 presented a distributed control approach in which each node within inverter computes the average of inverter frequencies and uses a PI controller to drive that frequency, the average frequency, to the nominal value. But this controller does not necessarily achieve proportional power sharing objective. Now, paper from 2015, they propose, so paper proposes the fair splitting scheme in which generators produce power according to their capacities, and the scheme is realized through the so-called ratio consensus algorithm, which basically computes power imbalance in the network in a distributed way. And there are a few more works on which take into account communication delays, packet drops, and usually they derive some upper bounds on the communication delays to guarantee stability. And these upper bounds, they need to satisfy some robustness criteria, which might involve solvability of linear matrix inequalities, which might be difficult to do in practice. So now we're gonna move to the main part of the presentation. We will present frequency control strategies over time varying communication networks. And for the control design, we will utilize tools from multi-agent optimization. And in this and the next slide, I will give some background material on multi-agent optimization. So basically in the multi-agent optimization problem, we have n agents. Each agent has its local cost, which is unknown to other agents. And two agents can communicate with each other if they are physically close. And their goal is to collectively minimize total sum of cost functions, local cost functions. And typical approach is to let each agent estimate solution of P0 using a gradient descent approach. And then the neighbors average their estimates via communications. So they basically solve this problem P0 prime. So xi is the agent I estimate of the solution. And they have also this additional constraint. So at the optimal solution, their estimates should be at the same point. And typical algorithms for solving this problem include two steps. So they have averaging step, distributed averaging step that ensures that estimates converge to consensual point. And then they also have gradient descent step, which steers that consensual point towards the optimal set. Okay, and several algorithms have been proposed to solve this problem over undirected communication graph. One example is distributed subgradient method, where basically agent I in the distributed averaging step computes the average of its estimate and the estimates of its neighbors, and then adds this gradient descent term. Now, if we use this method to solve problem over directed communication graph, unfortunately, the individual estimates may not necessarily converge to the same point. So, and the reason is that nodes which are more like centrally placed in the network, more strongly connected, they tend to place more weight on their information, and that can cause bias in the consensus.
You have not told us anything on how you pick those weights.
So,
AES. Have you said anything?
The average, so it's just, so these weights, they should sum up to 1.
Right.
Yeah.
So why is that that I didn't know, or that I didn't know that I thought that the necessary and sufficient conditions are that the weights form a doubly stochastic
No, this, I mean, this is the feature of this method.
But why were you saying that? something about the nodes being more centrally located. This might fail to converge to.
For directed communication graph.
But in the directed communication
Yeah.
graph, I thought that as long as the weights still form a doubly stochastic matrix, it doesn't matter. Is that the case?
No. For directed communication graph means that they don't necessarily exchange information during the same period.
So that means that
So one node's weight might be aij, but the other weight would be 0.
But
It won't be doubly stochastic.
It won't be doubly
Yes.
stochastic. Okay.
Yeah.
We're on the same page.
Yes.
Go ahead.
Yeah. And so to handle directed case, there is subgradient push method. So basically, instead of maintaining one linear iteration, it maintains 2 linear iterations and then computes the ratio to produce the final estimate.
Throughout here, you need to have references to who did this, okay?
Yeah.
As the usual citation.
Yeah. Yes. So this is this protocol, which is used in this distributed averaging step, is called push sum protocol or ratio consensus algorithm.
So can you explain the intuition behind defining this push sum protocol? That's quite obvious. It's
Like,
what is going on in push?
So in the push sum protocol, we choose the weight such that the mixing matrix is basically the column stochastic. Yeah.
So you ensure column stochasticity using a what is being used to ensure the column stochasticity? That's what it is.
So I was intending to say it in the next slide. So basically, this subgradient push method uses the assumption that each node knows its out degree at time k, which is not necessarily true, right? The number of nodes which receive information, in general it's difficult to know the number of nodes which will receive the information from you, right? But this method uses that assumption that you know how many nodes receive information from you. And based on that assumption, we choose the weight such that we form column stochastic mixing matrix.
You can get around that with what we call the robust ratio consensus. You keep more variables, and then you don't really need to know your throughout the degree. So that, yeah. So anyway.
Okay, so yeah. So now let's make a connection between multi-agent optimization and frequency control design, and we will look at the distributed averaging PI controller, which will help us better understand how to utilize the tools from the previous slides to the for the frequency controller design. So this controller has some interesting features, and it combines primary droop control functionality with the secondary frequency control functionality. So unlike traditional control systems in bulk power grid, it doesn't assume that these two functionalities are timescale separated. So it basically adjusts the frequency such that the power outputs of the generators track this reference, and then adjust the references such that the frequency error is eliminated and load sharing objective is achieved. And WI, W is a diagonal matrix where its diagonal entry is a droop coefficient. Any questions?
So who proposed this? Doppler and Porter,
Yeah.
right? So again,
Yeah.
we have all these references here.
Yeah. So primary droop and AGC basically.
Right.
Yeah. Now let's look at the discretized closed-loop microgrid dynamics of this controller. So we have basically iterations for the power injections, how they evolve, and this control signal which goes to the frequency controller and Xi, right? And the second iteration has well-defined distributed averaging step and gradient descent step. And we're gonna denote this matrix here by A, and we call it mixing matrix. But because of the presence of this matrix S, and because its sparsity structure does not necessarily coincide with the sparsity of the network, it's not obvious how to interpret these dynamics using multi-agent optimization perspective.
And this was the sure complement when you for the network once you did the regression, right?
Yeah.
So that's the S that appeared early on in the
Yes.
a few slides back. And you're saying that that does not coincide with I guess you have to go one slide back.
One slide
That
back.
doesn't go back. That doesn't coincide with the sparsity. That doesn't coincide with the sparsity structure of the graph Laplacian, right?
Yeah.
Communication graph
Yeah.
Laplacian.
Yes. And also its presence is not clear how we will interpret. Is basically like, yeah. So. And to conclude this slide, so there are a few limitations, and one limitation is that this controller uses bidirectional communication links, and information exchange at each iteration occurs simultaneously. However, in practice, this is not true, right? Information exchange is difficult to implement controller to communication protocols such that information exchange happens at each iteration because of the communication delays and packet drops. And also communication links can be unidirectional. Now, to basically make a connection with the multi-agent optimization, we consider the following linear transformation. And we introduce this variable p tilde, which evolves according to this iteration. So this iteration was chosen such that when you plug this into the transformation, you recover the original dynamics for the power injections. And now we see that with this new variable, these iterations can be written in terms of the gradients of cost of some cost function, which is shown here, and we call this problem P1. This is almost similar to P0 prime, except this P tilde. We don't know how to interpret P tilde yet.
So is this just the gradient, or is it you have the average in there via the matrix? No, this is just gradient, right?
No, this is gradient.
This is just gradient. Yeah, okay.
So one question. So can you go back one slide? This is your whatever Porco and folks have done. The distributed PI controller, you're saying that you can think about its dynamics.
Yeah.
It's trying to solve a centralized optimization problem of the following problem.
Yeah. Yeah.
And P1, you don't have a particular.
Actually, we're trying
is there
to.
an interpretation of that?
We're trying to formulate this multi-agent optimization problem. So not centralized, but distributed
But what is
optimization.
P1 trying to solve? Why do I even care also? That's my question. You see my point, right?
To achieve the objectives that we mentioned earlier, power sharing.
Right. So the solution of P1 via the solution of P1 via that gradient algorithm That gate algorithm is the dynamics of the DAPI controller.
So
That
the,
DAPI controller is achieving power sharing plus frequency optimization. So, I mean, your question, I think, is that are those two objectives somehow embedded here in the cost in the cost function here?
That's what.
I don't think so, but you
no,
correct me otherwise.
so this is the, if you recognize, is a injection, right? PI, right? So PI, and we have this constraint, right? All size should converge to the same value, right? So if you solve this problem at the optimal solution, all PIs should converge to, so PI will converge to DI times some constant.
And that's the power sharing.
That's
part.
the power sharing.
And
Yes.
then the GI.
And then when you do power sharing, frequency also will naturally converge to 60 hertz.
So it's a physical interpretation.
Yeah.
Oh, so you can actually, yeah, then I would suppose if you take those two as objectives, so forget P1 first. Take the objectives as power sharing
Yeah.
and minimum and
Frequency regulation.
and frequency regulation.
Yeah.
And then formulate an optimization problem.
Yeah.
You can, through some, if you formulate it in a particular way, you will end up with this.
Yes.
So yes, this is one of the ways to formulate.
Yeah.
Then you do have an idea.
Not yet because of the P tilde. What is P tilde? Here xi is the xi I, for example, is the generator I estimate of whatever they are estimating, right? But P tilde, what is P tilde? No, well, I'm gonna explain in the next slide. So let me, let's take a step back. So P tilde and xi, the goal of P tilde k and xi k is to estimate solution of P1. And in particular, xi I is agent I estimate of this quantity for power sharing, right? And we define this quantity by zeta star. And the average of these xi variables is the average estimate of zeta star. Now, I mentioned that the distributed averaging step ensures that all these individual estimates follow a certain average estimate trajectory, right? Or average process, which then will converge to the optimal solution. So we will view P tilde and process induced in microgrid. So basically, P tilde k is already average estimate of P tilde star. This is how we're gonna view, and this is important for the convergence analysis. Yeah. And as a final note to this slide, if P tilde k and psi k converge to the optimal solution, then the injections will converge to this pi star, which basically share the load according to these Drup coefficients, right?
So what do you have next? The proof of the algorithm, or
Closer look at the algorithm itself. So we mentioned that the algorithm assumes that information exchange happens simultaneously at each iteration. Now we will propose a way to resolve communication delays which might happen. So neighbors, and to do that, we need to basically recompute the weights in the mixing matrix A. So basically, if neighbors exchange information, we need to set the corresponding weights in the mixing matrix to a number which is greater some eta, where eta is some positive number. if generators I and j simultaneously exchange information during this time interval. And we also recompute the corresponding diagonal entry in the mixing matrix such that AK is doubly stochastic. Yeah, so we can write the dynamics in this way where A is a time varying matrix. Okay, and still we have a limitation. Information exchange needs to happen simultaneously, which we're gonna address later. So in a similar way, we can apply this subgradient push method to design the controller. So we have two linear iterations. The ratio of these two linear iterations will give us psi I for generator I, and we use this psi in the frequency controller, right? And here there is a limitation also. Each node j needs to know its out degree. Yes. Now for the convergence analysis, we need to make additional assumptions. So we need to assume that the microgrid is lossless, and we will fix S at equilibrium point. So S is symmetric, constant, and positive semi-definite. And in our first result, we show that these dynamics converge to the optimal solution if the step size alpha k satisfies these two conditions. And we have a similar result for directed case. The only difference is that the step size needs to be monotonically non-increasing. So let me give the.
I have a quick question.
Okay.
So
Yeah.
take the proof of a push sum protocol.
Okay.
Is there any particular aspect where this sort of differs? That is, your algorithm, the way you are developing it, is it directly applicable, or you need some more adjustments because certain additional terms are there?
I didn't understand your question, Professor
So
Bose.
suppose I take push sum protocols proof, right?
Yeah.
It's already there in the video. Now, if you interpret this algorithm, certain variables and certain other variables of that, does the proof follow, or you need to unpack and do something more because of maybe something doesn't abide by the assumption?
So we remember that p tilde, so that comes into play. So we use that linear transformation.
And the sparsity structure is not the same.
Yes. So we interpreted p tilde in some specific way, which basically allowed us to use those optimization tools. Yeah. And also for this, the convergence analysis is for symmetric and positive semi-definite matrix. Losses, we yeah. But in the numerical simulations, we use lossy microgrid.
So is robust push sum
Push sum, yeah.
protocol, has it been pretty well analyzed? That is, suppose communication errors happen with the push sum protocol. Is it analyzed whether it converges or not, or whether there?
Yeah, it asymptotically converges, right? Yeah, but not exponentially, not geometrically.
The convergence may not be known. So rate of convergence is not well understood.
Yeah.
But, in terms of convergence, you can get.
Rate of convergence, Professor Bose, is only asymptotic, so it's not geometric convergence.
And so usually what happens with these kinds of non-summable, square summable,
yes, they are
square summable sequence step sizes.
Yeah.
You can get convergence result. That is, it converges, period.
Yeah.
But you can't say how fast.
Yes.
very difficult. Even subgradient has the same problem.
Usually it's now if we consider convergence within some error, it will be geometric. It will be geometric.
But there are ways to do
Yeah.
I would skip the
The
proof,
okay.
Madi, because we're a little bit
Yeah.
constrained with time. So just skip the proof.
So let me go back to undirected case. So I talked about this distributed subgradient method, right, with simultaneous averaging. And here I will propose another approach that doesn't rely on that assumption. So information exchange does not necessarily have to happen simultaneously. And in order to achieve this, we let each node, each generator to, instead of maintaining only one estimate of that quantity, zeta star, if you remember, we maintain one estimate for each communication link. So for example, in this network, node 1 maintains one estimate for link 1, 3. And these estimates are updated separately, so all distributed averaging steps are completely decoupled. Performs averaging with node 2 to update the estimate corresponding to link 1, 2. However, we still to the same point, right? So we do that through local averaging, and this local averaging will be included into gradient descent step. So basically, in our optimization problem, we will include additional local averaging objective to drive all local estimates to the same point. Now, this you might say that this case is a special case of directed communication graph, right? Because links are now unidirectional. We can assume unidirectional. But in directed communication graph, for any given pair of nodes, if one node is physically capable of transmitting information to other node, it doesn't necessarily mean that the second node will also be capable, right? Because communication ranges can be different. Yeah. Any questions? But this is still important special case of directed communication graph.
Maybe skip all this part because we have only 15 minutes left, and please.
Yeah.
Skip all this part and go to the next part.
To the next part.
Yeah.
Numerical results.
Yeah, that's good.
So for undirected case, I consider this 9-bus microgrid with 3 generators. Each generator in the simulations is modeled as a controlled voltage source with adjustable voltage, magnitude, and frequency. And all lines are lossy, and all loads are PQ loads. And this is the cyber layer. So all 3 generators are mutually connected. And communication links fail with probability 0.25. And these are the inverse droop coefficients. So generator 1 needs to produce as much power as the total power produced by generators 2 and 3. And we also have a voltage controller, which basically solves some kind of optimization problem to ensure that all voltage magnitudes are within operational range. So in this figure, as we perturb load, so we have perturbation perturbations. And as you see, the power injections, they converge to the point where they share the load according to their droop coefficients. So generator 1 injects as much power as the total power injected by generators 2 and 3. And we also have frequency which goes to 60 Hertz. Now here we see that as a result of load perturbation, voltages drop below operational limit, and this triggers the voltage controller, and then the voltages start to increase. They are restored to normal operation, and then frequency controller still is able to achieve its objectives. And in some cases, the convergence speed was almost like geometric convergence, but here we see it's more like asymptotic. And here I use constant step size. So I haven't used diminishing step size.
But you have to for convergence under constant step size?
No, it will converge within some error. Yeah, for constant step size. And for directed case, yeah, I perform the same numerical simulations. So this is the cyber layer for the directed case.
Frequency goes back to nominal pretty well. So even if they show that within an error, you are solving it pretty well.
Yes, so that's my. Still, I don't know. Does the step size need to be diminishing? Maybe for this problem, the constant step size will actually ensure the convergence. And I think the convergence is geometric almost. So in the next part of the presentation, I will talk about the coupled phase oscillators and their applications to power systems. So this model consists of second order oscillators with Newtonian dynamics, and in power systems they correspond to generators, and the remaining oscillators are basically feature first order dynamics with some time constant, and they correspond to loads. So these oscillators widely used to describe dynamics not only in power systems but also in mechanical and biological networks. And these oscillators basically represent a group of particles, and each which rotate around the unit circle. Each particle can be characterized by the phase angle theta I and the angular frequency omega. And they are connected through these elastic springs of stiffness A, Ij. And the question of interest is under what conditions do these oscillators synchronize so that they rotate at the same speed and angular difference between any two connected oscillators is less than some value. And this paper here presents a synchronization condition, which basically tells us that if the natural frequencies and stiffness coefficients satisfy this condition, then oscillators will synchronize such that the angular differences are between connected oscillators is less than or equal to gamma, and gamma is less than pi over 2. For radial power networks, what this condition really means is that power flow along each line needs to be smaller than its physical capacity so that generators can synchronize, which is obvious result. Now, in the context of power systems, if the injections satisfy this synchronization condition, then voltage phase angles are cohesive, right? And I forgot to mention that if phase angles satisfy this this condition, then they are called cohesive phase angles. So we utilize this synchronization condition to basically design a controller that achieves tracking of optimal reference computed by after solving an optimal power flow problem. Because in general, if this reference is far from the current operating point, local stability analysis does not necessarily provide us with correctly working controller. So we show that if the current operating point and the references satisfy this strict version of synchronization condition, then there exists a controller that makes the power outputs of the generators track the references. Is it clear or? And the stability analysis will be large signal, so this controller achieves regional tracking, right, of the reference. There are possible benefits of this controller. During the execution, we don't violate thermal constraints. Disturbances along critical lines are reduced, and we also have more robust performance. So the main idea behind this controller is basically use intermediate reference PR and not to let the power outputs of the generators deviate too much from the straight line connecting the current operating point and the reference. And to achieve that, we utilize this intermediate reference, and the idea is to set this reference at some fixed distance from the current operating point and let this controller run. Once the power outputs converge to this intermediate reference, we move it along the straight line to the next point, and we let the controller run again, and that eventually the power outputs of the generators will converge to the reference point. Choice of this delta is choice of this delta, the radius of the ball is critical because any point inside this ball basically satisfies the synchronization condition. And no matter how power outputs of the generators evolve, as long as they are inside this ball, the phase angles will be cohesive. Yeah. So, any questions? Yeah.
How do you
choose the size of the change in power movements?
Based on this delta, the radius of the ball. So in the next proposition, we compute the exact precise value of delta for lossless microgrids. For radial lossy microgrids, you can approximately compute the value of delta. Now for cyclic lossy microgrids, the power outputs of the generators will not necessarily converge to the set points because of the circulating currents along the cyclic path. Yeah. So.
Yes, let's stop here.
Yeah. Okay. Thank you.